Hello, and welcome to our talk, Securing Tesla and Mobileye from Split-Second Phantom Attacks. This is a joint talk, and I will present the first part of the talk. My name is Ben Nassi. I'm a Ph.D. student from Ben-Gurion University of the Negev, and the second part of the talk will be presented by Dr. Yisroel Mirsky, a postdoctoral fellow from Georgia Tech. Okay, now this talk is based on 3 papers that were published at CCS and at AutoSec 21 workshop, and you can find them online. The first paper, which is named Phantom of the Ages, was presented at CCS, and it consists most of the information is provided in this talk. So let's start to discuss about perception of computerized driver intelligence. And virtual perception is the ability to interpret the surrounding physical environment using algorithms that obtain data from various sensors. And virtual perception of semi or fully autonomous cars usually consists of algorithms and hardware structured in 4 layers. And as you can see on the bottom, there is a picture taken from the dashboard of Tesla with the full self-driving functionality. Now let's understand exactly how virtual perception, the layers of virtual perception. Now the lowest layer is the layer of the sensors. Sensors are radar, video cameras, ultrasonic sensors, LiDARs, and GPS sensors. On top of this layer, just before, sensor fusion is usually the most commonly used approach that is being used by the car industry. And the reasons is that sensor fusion is used to increase accuracy, provide redundancy, and increase the overall robustness of the semi or fully autonomous car. And the combination of sensors used varies among car manufacturers. For example, Tesla includes front-facing radar, a set of video cameras, and a set of ultrasonic sensors. Yandex self-driving cars, on the other hand, include radar, LiDAR, and a set of video cameras. Now, on top of this layer, there is the sensor refinement layer, which consists of algorithms that are used for filtering and alignment and some digital signal processing that is being done. On top of this layer, there's the object refinement layer. I will speak about object detectors in a few slides from now. And the last layer in perception is the situation refinement, which mainly consists of assessment algorithms, which intended to assess the intentions of the nearby objects, for example, the pedestrians or the nearby cars. And virtual perception, as I mentioned before, consists of these 4 layers. Hardware and algorithms are combined together. Now, the research around virtual perception started about 40 years ago. On the left side of the timeline, you can see the prototype, which was a Terregator, which is a road-following robot that was developed at CMU. 40 years later, basically today, commercial semi-autonomous cars, we're in the era of commercial semi-autonomous cars. Teslas are about to acquire level 3 capabilities with the addition of the upcoming full self-driving functionality. And somewhere in the future, we are about to see fully autonomous cars that drive without any manual involvement. Now, I think that you will agree with me that virtual perception has improved significantly over the last 40 years. Now, don't get me wrong, there are still open challenges for virtual perception. One example is acquiring level 4 and 5 capabilities. For example, driving in unknown or unmapped areas is still considered a complex task. Also, the science needs to find a way to overcome some perceptual challenges, and some well-known fatal accidents demonstrates the perceptual challenges that ADAS still have. In these 2 well-known fatal accidents, Tesla's autopilot drive directly and crashed to parked cars that park on the side of the road. And these pictures are taken from the accident. Now, also there are the adversarial AI attacks, which also emphasize the difference in the perceptual challenges that we are currently facing. And I wanted to discuss about adversarial attacks. And adversarial attacks in our context are physical objects that are perceived differently by AI than by humans. And previous studies showed that by adding a physical artifact to an existing object, it causes the object detector to misclassify the detected object. And it was done by adding stickers, it was done by adding graffiti, it was done by printing road signs with black color, as you can see in the picture on the right side. However, we are hearing about adversarial attacks for the last 5 years. An immediate question that arises is, why haven't adversarial attacks been observed in the wild? And we try to think about several reasons about the disadvantage of adversarial attacks. And one reason is because the adversarial attacks require the attackers to approach the attack scene, which is something that attackers would like to avoid. Also, some adversarial attacks require skilled attackers. Some of the attacks require understanding or deep understanding in data science, which mainly limits the amount, limits the people that the type of the attackers that can apply these attacks. Other attacks are basically white box attacks, which means that they demand full knowledge of the attack model. Other attacks leave forensic evidence in the attack scenes. For example, stickers may help the police to find the attacker. And also, some of the attacks require complicated preparation. And for those of you who have trained a neural network or an adversarial neural network, it is somehow a very complicated preparation in order to train a model that can output an adversarial instance. Now, I want us to spend a few slides in order to understand how computer vision identifies objects in a picture. And object detectors are algorithms which are used to identify the location of instances of objects of a certain class. This can be pedestrians, it can be road signs, it can be, for example, cars. And object detectors receive frames as input and output a set of bounding boxes with classifications of associated objects. And in this slide, you can see on the left side a pedestrian object detector. In the middle, you can see a car detector, and in the on the right side, you can see a road sign detector. And object detection starts with a string of frames, and as was indicated before, the object detector receives frame as an input, and boundaries of objects are detected and suppressed to remove duplications of the same object. Now, this component is mainly relies on several architecture. Now, for example, the YOLO is a famous architecture. There are some others interesting architecture that are being used for the to detect object inside a frame. And there is an algorithm which is used to suppress or to remove the duplications of the same object, which is followed by the object detector. However, these two components are very or well known to most of the people. There is another component which is called the persistency function. This component is not exactly known to most of the people. And a persistency function is a component which is used to decrease false positive detections by verifying the existence of a detected object in a few consecutive frames. And a persistency function works as follows. Given a detected object, it verifies whether its duration is greater than a predefined appearance duration. And if its duration is greater than the predefined appearance duration, then the persistency function accepts the object as a real object and classified as a real object. Otherwise, the object is rejected and considered as false positive. Now, as you can understand, using a higher appearance threshold will result in a lower false positive rate by the object detector. And this is a commonly used practice in the area of time series. You can set the desired false positive rate by increasing the appearance threshold. However, in our context, real-time driving requires that objects, for example, pedestrians, be detected as quickly as possible so that the car immediately reacts to them. So you have a trade-off point where the appearance threshold is set by the manufacturer based on its experience by taking both constraints into account. The appearance threshold must increase the false positive rate, but it should be short enough to detect objects, and in our case, it's milliseconds for driving cars. Okay, now only objects that appear for a period of time greater than the appearance threshold are considered by the persistency function, and they are objects that appear in the detected area. You can see in here as the green area. And we ask this question: can we apply a split-second attack that appears in the detected area but is imperceptible to the human eye? Or in other words, can we exploit the time domain by applying an attack with a duration that is slightly longer than the appearance threshold? And this is where we will start to discuss about split-second phantom attacks. Now, split-second phantom attack is an attack where the attacker presents a phantom object to a car for a split second. And this phantom triggers an undesired reaction from the car. Now, this can be done by projecting the phantom object from a drone, or this can be done by hacking an internet-connected digital billboard and embedding a phantom object into an advertisement, into an existing advertisement. And the significance of this attack with respect to the previously suggested or discussed adversarial attacks is that split-second phantom attacks can be applied remotely. They do not require the attacker to approach the attack scene. They also do not require any spatial expertise. They do not rely on white box approach. They do not leave any evidence at the attack scene. They do not require any complex preparation. And finally, as opposed to the adversarial attacks that exploit the space domain, split-second phantom attacks exploit the time domain. Now, why does a commercial ADAS, advanced driving assistance system, detect phantom object? Now, here is an experiment that we did. We projected a road sign on a tree. You can see it in the picture on the left side. And we placed a car which was equipped with Mobileye 630 in front of this projected road sign. Now, here is an interesting fact. Mobileye 630 Pro considers the projected road sign a real speed limit sign. And some of you are probably not that surprised because Mobileye 630 Pro consists only of a video camera. Now, we made another experiment. We took the picture of Mr. Elon Musk and projected it on the road. And we placed Tesla Model X in front of this projection. Now, here is an interesting fact. Tesla Model X, which was with hardware 2.5, considered the projected person a real person. Now, despite the fact that this car is equipped with radar and ultrasonic sensor that intended to detect death. And you can understand that this picture is completely deathless because this is the result of a projection, but it is still detected by Tesla Model X. And we repeated the same experiment, however, this time with a projection of a car that was projected on the road. And again, here's a fact: Tesla Model X with hardware 2.5 considers the projected car a real car. This is despite the fact that the car have greater radio signature than a pedestrian. So you would expect that the radar to ignore or to ignore this or consider this classification as a false positive. However, as you can see on the left side, the picture that is taken from the dashboard shows that it is considered as a real car by Tesla. Now, I think that you will agree with me that there is a difference between what an ADAS thinks it is and what is actually there. And the three following pictures demonstrate. Now, I want to mark that we don't consider phantoms as bugs. They are not the result of full security implementation. They are not, for example, an SQL injection. Phantoms exploit the fundamental inability of object detectors to distinguish between real and fake objects. And we consider phantoms a scientific gap. So why are phantoms a scientific gap? Object detectors are the output of a long training process. And previous studies have already discussed the implications of using training process to create AI. And they discussed about the high level of computing capabilities, and they discussed about the high energy consumption, and they also discussed about the high cost and the long training time. However, it seems that in the context of autonomous driving, it seems that the training process creates robust AI models that function better than humans in real life. And you can see the articles in this slide were taken from about 2 years ago. Tesla 2 years ago was considered, Tesla's autopilot was considered 9 times safer than the average driver. It was about 2 years ago. However, we try to ask a different type of question. What object detectors don't learn? And we tend to understand that the following 3 characteristics are not taken into account or aren't trained or aren't learned by object detectors. Now, the first one is context. You can see how unrealistic objects are being considered by advanced driving assistance systems. A road sign that is projected on a tree is, of course, unrealistic object. However, it is still being detected by Mobileye 630 Pro. Also, in some cases, colors aren't taken into account. This road sign consists only of gray colors, and it is still being detected by one of the state-of-the-art object detectors currently exist. And also texture in this case isn't taken into account. You can see how transparent and in some cases even skewed objects are still considered by advanced driving assistance systems as real objects despite their texture. And object detectors, we concluded that object detectors are essentially feature matchers. They lack the ability of humans to ignore fake or inauthentic object. Basically, they consider an object if it is similar to the objects that appear in the data set that they were trained on. Now, let's try to understand how attackers can exploit this fact and apply the attack. And the first experiment that we did is we tried to detect the appearance threshold. And in order to do so, we used two road signs. For Tesla, we used a stop sign, and for Mobileye, we used a speed limit. And we flashed this road sign at various durations in front of this, in front of Tesla, in front of Mobileye 630. And you can see the results on the right side. And we found that Mobileye 630 detects a phantom road sign in this case, that appears for 125 milliseconds, 100% of the time. And the case for Tesla is somehow different. Tesla detects a phantom that appears for 416 milliseconds, 100% of the time. Tesla have greater appearance threshold than Mobileye. Now, at the beginning, I explained about remote attack models that can be used to attack advanced driving assistance systems. And one was to mount a projector to a drone. And in this experiment, we mounted a projector to a drone, and we used it to flash a road sign for 125 milliseconds on the building on the right side of the road. And the driving car was equipped with the Mobileye 630 Pro that detected this phantom road sign as real road sign and notified about it to the driver. We also conduct another experiment for Tesla Model X, and in this experiment, instead of using a road sign, we used a phantom of a pedestrian. We projected the pedestrian on the road from the side of the road using a projector, and we didn't use a split-second projection, mainly because due to safety concerns. And you can see how the car detects the pedestrian and immediately and automatically reduces its speed from 14 miles per hour to 18 miles per hour. And you can see it again, the car is driving at 18 miles per hour, and right now it decreases speed because it detects a pedestrian. Now, finally, there's the second way to apply the attack, which is to apply it via a digital billboard. And many digital billboards nowadays are connected to the internet, so attackers can hack the digital billboard and embed a phantom into an existing advertisement. And we developed an algorithm to embed a phantom into an existing advertisement in a hidden way. We take any given advertisement, and for the given advertisement, we compute a local score for each and every block in every frame of the advertisement. And the local score for each block is computed as follows. We extract key points for each and every frame, and we compute a local score for each block based on how much a dead area the block is. It means basically on its with respect to the key point that was extracted, basically on how distant the block is from the extracted key points. And we also compute a global score for each and every block. And the global score is computed with respect to the score of the block in the subsequent consecutive frames. This is done in order to take the time domain into account, because in some cases, a phantom needs to be embedded to a few consecutive frames in order to meet the appearance threshold that is defined in the advanced driving assistance systems. And this is a demonstration of the output of the algorithm. We took an arbitrary advertisement and embedded a stop sign to the advertisement according to the output of the algorithm. You can see the stop sign right now. It is being flashed for 500 milliseconds. And we took this advertisement and presented it on a digital billboard in an experiment we conducted, and we engaged Tesla's autopilot. And as you can see, Tesla detects the phantom stop sign and immediately stops the car in the middle of the road, despite the fact that it's not a real road sign. You can see it right now. This is where the phantom stop sign appeared on the left side of the advertisement. And you can see the dashboard where Tesla detects it as a stop sign and immediately triggers the car to stop in the middle of the road. Now I will let Yisroel to continue the talk.
Thank you, Ben. Hi, everybody. My name is Yisroel Mirsky. I'm a postdoctoral fellow at the Georgia Institute of Technology, as well as a research project manager at the Ben-Gurion Cybersecurity Research Center in Israel. Now that we've seen the vulnerability and understand its implications, let's talk about what we can do to strengthen our AI systems against such attacks. In other words, how can we close this gap between the AI and the human driver? Now, even though autonomous vehicles use sensor fusion, for example, radar and LiDAR, the autonomous system will still react to objects detected in the images alone. However, this makes sense if you think about it. If the AI detects a person in the middle of the road based on the camera alone, you're going to react because you don't want to cause a fatal mistake. Therefore, we need a solution which can validate objects identified by the camera sensor's AI, We also need the solution to be independent and lightweight so that we can easily integrate it into existing systems. So how are we going to do this? Well, we thought about this a lot, and we tried to think of reasons why a human can tell the difference between a flat projected image and AI cannot. We then understood that an object detection AI has been trained to do one thing only: identify objects by matching patterns in geometry. In contrast, a human's intuition will raise a red flag if certain aspects or contexts are right. For example, on the right, we can see that Google's Cloud AI is convinced that this hairy amorphous blob is a cat, just because it has fur, eyes, and some pointy ears somewhere in there. Of course, we still love deep learning models, but we just want them to be a little bit more intelligent. Until then, what will we do to identify these false objects detected by the camera? Well, instead of throwing another classifier at the problem, which will fail for all the same reasons, we will first take a look at the detected object and then analyze different aspects of the object to determine if it is real or fake. We've identified 7 aspects which can be extracted from an image to better capture the truth. Let's look at the attack scenario where a phantom road sign has been projected near the car. First, we can consider if the size of the sign is larger or smaller than it should be, then it might be problematic. For example, a traffic sign which is not regulation size should be ignored. The size of the sign can be determined on vehicles which use multiple cameras through stereoscopic imaging. Second, we can look at the angle of the sign. Cameras capture perspective, so the shape of the sign does not match. If the shape of the sign does not match, then we can consider it being fake because it is being projected on an angle facing away from the car. Third, we can look at the focus of the sign. A projected sign may be blurrier than its surroundings if the projector is out of focus, or partially blurry if it is being projected on an uneven surface. The focal range of the camera can also be used to identify range whether the sign is contextually, and understand whether the sign contextually makes sense. Speaking of context, if the placement of the sign is impossible or simply abnormal, it indicates that it is a phantom. For example, a traffic sign that does not have a post or some pedestrian floating over the ground. We can also consider the surface of the sign, if it is distorted, lumpy, or has features which do not match the typical features of a detected sign. For example, think of what a stop sign may look like if it were projected on a brick wall. Another aspect is light being emitted from the sign. Since phantoms emit their own light via the projector or TV screen, they will be inherently different compared to the light reflected from the road from a regular road sign. This can be determined passively through image analysis or actively by shining a light source onto the object. Finally, we can consider the depth of the scene. We can detect phantoms if the object has the wrong surface shape or its placement in a 3D scene is abnormal. For example, a traffic sign projected onto a tree or a 3D person or car projected on the surface of the road. However, how can you get the depth perception from a single camera? So we use a technique where we take a look at 2 subsequent frames captured by the camera. If they are captured while the vehicle or projection is in motion, then we can compute the depth implicitly using optical flow, much like stereoscopic viewing. To give you a better idea of what I'm talking about, here's what it looks like. On the left is the first frame, then using the second frame, we can compute the image on the right. The directional shift between the pixels is the color, and the brightness is the speed. Now imagine what a person projected on the road would look like. It would be a solid flat color, just like the rest of the road. This is a strong indication of a phantom compared to a real person, which would produce a distinct shape. So how do you utilize multiple perspectives without falling into the same traps as before? So we suggest using a machine learning ensemble approach called a committee of experts. The idea is that you use a diverse set of models on the same image, where each model has a different perspective on the image. Then you combine their predictions by considering each of their viewpoints. What is key in a committee of experts is that there be disagreements. These disagreements help the ensemble produce more robust predictions. To evaluate this approach, we developed this detection model called Ghostbuster. Here we only consider 4 of the 7 aspects: context, surface, light, and depth. The way the system works is as follows. When the onboard object detector identifies an object, say a road sign, the cropped image is passed to our model for verification. Then 4 different aspects are extracted from the image and passed to their corresponding experts. The experts reason whether the object in their perspective makes sense or not. Finally, The internal representations, also known as embeddings from each of these networks, are concatenated and passed through a single network, which makes a decision based on the expert's feedback. Although this model may seem intimidating, it is important to note that it only has 1 million parameters, which is nothing compared to the hundreds of millions which object detection models use. Therefore, adding this model to the system as a guard has a negligible impact on the car's resources. When evaluating 7 state-of-the-art object detectors, we found that the models were susceptible to phantom attacks with a 92 to 99% attack success rate. However, with the defense model in place, the attack success rate dropped to below 1%, even when tuning the model to have 0 false alarms. Below, we can see here the committee at work. The table shows that every expert has a useful and unique contribution, where the combination of all experts outperforms the baseline model, which in this case is a single classifier. Here are some visual examples of these disagreements, which ultimately lead to correct classifications. For example, here in the top left, the context expert found it strange for a speed limit sign to be over the highway, but the light expert identified it as a digital road sign. Okay, so we know that the model is robust to the environment, but is it robust to the adversary? In other words, what if the attacker uses adversarial machine learning to fool our defense model? We attacked our model with 8 different adversarial machine learning attacks. Through these experiments, we found that the committee as a whole is much stronger than any single expert. This is because the combiner model can identify an outlier when only one of these aspects have been altered. This makes it significantly more challenging for an attacker because some aspects cannot easily be altered, like depth and lighting aspects. So in summary, there exists a perceptual gap between AI and human drivers. And this gap can be exploited by an attacker, even with sensor fusion in place. However, if we can force our models to consider multiple aspects or perspectives on the data, then we can mimic a human's intuition and close this gap further. So how can we apply what we've learned in this presentation? For future systems, we should always consider redundancies when developing safety-critical AI systems, especially if the AI subsystem has a direct control over the system's behavior. Some lessons we can learn from this are, 1, we should analyze the edge cases of an AI model and by trying to answer the following questions. What did not appear in the training set that the AI model could encounter in the wild? And what did the model really learn? 2, we should test the robustness of our AI models by providing edge cases. And 3, we should secure our AI models by retraining the model with edge cases, and we should make sure we add features or perspectives that distinguish between good and bad cases. That's all. Thank you for joining our session.